All right, so let's start. First, there's an announcement. There's another colloquium talk today. I don't know if anybody tried to go to the last one, but it turned out they moved the room at the last minute. So if you did try to go, you would have found the wrong thing there. Had to search for the correct room. Did that happen to you? Happened to me. I showed up at the colloquium 15 minutes late. This one today, I think it's very unlikely to be moved. So here's the location. January, it's today, 2:30 in Thompson 119. And this colloquium is by somebody named Bianca Baire. She's at Brown University, and she's going to talk about something called the local to global principle, which is kind of related to what we're going to start talking about today, which is congruence is mod n. So despite maybe very little of this being things that you're familiar with, what that talk is about is the idea that if you have an equation such as, I don't know, x squared plus 3 xy minus 17 xy cubed equals 4, you might wonder, does this have any integer solutions? And if you were to take that equation and reduce it to modulo a prime, which maybe that, I don't know if that means anything to you yet, but if you found it had no solutions modulo a prime, then it couldn't possibly have any solutions. Because if you have an integer solution, you can reduce the solutions to get a solution modulo a prime. So let me give you a really simple example of this sort of phenomenon. Look at this equation right here, x squared plus y squared plus 1 equals 0. Does it have any solutions with real numbers x and y? No. Definitely doesn't. Because if you take x squared and y squared and add them together, you get a non-negative number. And if you add 1, you get a positive number, so you can't get 0. So what this talk is about is working with numbers mod p, or mod p to the n. It's an analog of this observation. And it turns out there's something called the local to global principle, which in many cases says that a generalization of this observation that this can't have any solutions of the reals is enough to allow you to tell whether or not certain equations have rational or integer solutions. Anyways, that's what that talk is about later today. Okay, so that's the first thing. Second, I'm reminding myself to turn on this screen recorder right here. I haven't yet I recorded the last time, but I think I forgot to record the audio, so that wasn't very useful. But this one should work today, and in future I should have recordings. Okay, so we'll do that. Let's do status reports really quickly, and then what I'm going to do is tell you about the first homework assignment. I'll go over the problems, and then we'll talk about congruences. Okay, so first let's start with status reports. Let's start on this side this time. Status report. What have you done relevant to this class since the last class?
I made some progress on my quantization conditions.
Okay, cool, good. Yes?
Chapter 2 and homework lab.
Okay. Okay, cool. What
I read chapter 1 and then I started researching topics for my projects.
Excellent.
In the middle of chapter 2.
Cool.
This class.
Okay, well you made it today. Yep.
Downloaded the book and looked at it.
Cool. What have you done?
I start reading the book.
Okay, good.
I got through about half a chapter 2 and I went through a bunch of sections.
Excellent. Yep.
I did problem 1.
Of the homework?
Yeah.
Cool.
I started
Excellent.
I read
Great.
the book.
Cool. Yep.
Reading instructions, postage.
Okay.
I did tutorial.
Great.
I did much.
Okay. Yep.
Well, I start reading chapter 2.
Okay.
I read a little bit.
And what?
How to use a collaborator.
Oh, cool. Yep. Okay.
Started with
Okay.
I read some of chapter 2 and I did all the homework for my other classes.
Great. Awesome. Okay.
I created a project in Media Collaborator.
Okay, good.
I did the same thing and also looked at chapter 2, but I'm not sure. How do I know if you got my invitation to be a collaborator?
Let's just look. What's your name?
Matt, hi.
Matt. There it is.
Okay.
If you, I haven't actually set up a whole invitation system so much. You can just add anyone and they're added.
Okay.
If they're a user, they just get added automatically. If you put an email address of somebody in who doesn't have an account at all, then they'll get an email invitation. And when they join, then they'll be on the project. So, but I haven't been, like right now you could add everybody in this class if you wanted to a project, and they don't have to say yes or agree in any way.
Okay.
So, okay, next.
I read chapter 2.
Okay. Okay, great. By the way, I have a shared project which probably only has about half of you on it. So if you look in your account and you don't see this project called Shared Math 480, then let me know, for example, right after class or something, and then I can just add you to it. In fact, anybody, by the way, anybody in this class who's on this project can add anyone else to it. All you have to do to add somebody is just go to Shared, click on Settings, and then type their name or their exact email address here. So if you have a friend who's already on this project, you can just have that person add you. But also I can add you as well. Yes?
Question is, do we do the homework on the shared project or just
No.
copy the homework?
Yeah. I'm going to, at some point in the near future, I'm going to make it so that the homework magically appears in your project, but temporarily you'll have to copy the homework over. And I'll show you how to do that in a second. Don't do it in the shared project, because then it'd be like everybody in the class doing it together at once, which probably wouldn't be good. Okay, so next in the log. So we're done with status reports. So now I'm going to tell you about the first homework assignment. Just say a few words about the instructions and the problems. Let's see. Okay, so this is the first homework assignment. Due to the potential of procedural issues about how do you turn it in and so on, and things not being potentially sufficiently clear, I have made it fairly short. However, the last problem involves your project and could take you a lot of time depending on how much effort you put in. And if you feel like you're not getting enough practice with the material of the course, there's additional problems at the end of each chapter in here, which you can do. Some of which have solutions, I think, at the end of the book. So if you want to check your work, there's lots of solutions at the back of the book for the problems in here.
Like, do we have to memorize or understand every single piece of theory of the book?
Definitely not.
Like that? Yeah, I already checked.
So just as a reminder, there are no exams in this class at all. So memorizing stuff from the book's just completely unnecessary to get a perfect grade. Yeah. It's not that kind of course. There are courses that's a useful skill to do. I mean, it is actually useful to memorize things, but it's not something you have to do in order to do well in this course, because the evaluation is entirely based on your homework grades. What you need to do is turn your homework in on time, and every single time, well, you get 2 are dropped, but you don't want to slack off. You can be super smart, but if you totally slack off, you get an F in the class easily. So that's what matters. But memorizing stuff doesn't. It's very important in many, many things in life, and in number theory, but not necessary for this particular course. I recommend it, but hopefully that's clear. Okay, so let me just quickly go over the actual problems, and I'll say a few things about how to do them. So here's one, computed GCD by hand. Looks like somebody already did it here in the shared project. Maybe I'll delete that. So when I'm giving the lecture, I'm giving it out of the shared project. So if you want to pull up in your laptop, you could open this worksheet right now and type something if you wanted to, just so you know. Okay, so that was problem 1, do a GCD by hand. This one is to make a conjecture about primes. So there are 2 steps here. First, I define a function psi of x, which counts the number of primes of the form 4 times k minus 1. That is, the prime can be written as 4k minus 1 for some integer k. So roughly half the primes maybe can be written that way, or maybe a third, whatever. So compute some data somehow, and then make a conjecture about what the limit of that quotient is, and just state it precisely as a guess. And then second, search around, maybe in a book, maybe on the internet, maybe Wikipedia, whatever, for information about this function that I happen to have called psi here. And then once you have something, you should be able to, based on what's there, deduce what this limit is. Okay? You don't have to prove anything. You don't have to prove like a theorem that you look up somewhere else. Just say I read somewhere that psi of x has the following property, therefore this limit really is blah. Okay. And if you're bored and the homework's too short, you could do the same problem for k plus 1. Instead of -1, put +1 there. Here's some problem that just asks you to prove a few little things about GCDs. Just kind of practice working with the definition. Yes?
For number 2 from the last
Sure.
one, it says prove or disprove. Is that going to be a formal proof or kind of like, hey, look at this? Like more of like
Should be kind of formal.
Okay.
Yeah.
Just making sure.
Yep. For example, if you conjecture the limit is 0, and then you look up something online which says that psi of x, is I don't know 2/3 of pi of x, then you'd say, oh, it's formally, if this statement's true, then my statement's completely wrong. That sort of thing. It's hard to imagine a very formal proof for this particular question, though. But be careful. Okay, so here's one just involves proving something about squares. So if you have a perfect square, it cannot possibly be written in the form 4k plus 3. So like the number 9 is not of the form 4k plus 3. So it's just a problem, and there's a hint about proving it. Here's a problem about Mersenne numbers. So here's a Mersenne prime, and that's the biggest known prime. And what I want you to do is to come up with a way to compute the first few digits rather than the last few digits. I'm going to say something in a minute about how you can instantly compute the last few digits of this. But what I want you to do is compute the first few. And by quick, I mean really quick. It shouldn't take 10 seconds. It should be like that. Here's one. Find integers x and y so that 2014x plus 480y equals 2. The way I've written this problem, you could just make like some really stupid brute force approach to solve this, but you probably don't want to, since there is a good approach to this that involves the Euclidean algorithm. And there's a systematic way of solving this. It's better to understand how that works. And then there's a question, are there integers x and y so that blah plus blah is 3? That should be, that's something you can solve by just thinking about congruences. Okay, now finally, your project, I want you to come up with 3 different ideas for what you might do a project on. And I just give you some ideas for places to look. Okay, partly this is just an exercise in thinking about the range of different things. So even if you're like totally settled on one thing that you want to do a project on, still for this problem you have to come up with 3 different ideas. Okay, so good practice in thinking creatively about what the heck this course might be about and what might be interesting in this course. So you can do a lot of things, like you could take this book and flip to a random page and then start reading, see what happens. You could just browse the word number theory, look for number theory articles in Wikipedia or on Google and see what happens, etc., etc. There's lots of things you can look at to try to come up with ideas for projects. Okay. So those are the problems, and then I want to streamline this some more, but there's some programming required to do so, and I haven't done it yet because I was busy with other programming. So what I want you to do is to just go through the worksheet, and like somebody did here, yes, illustration, here's an answer to that problem. That's how it was done, by just typing it in the blank. Get rid of that. So one thing, if you want to typeset mathematics, you might want to use what's called markdown mode. It's kind of convenient. I'll just illustrate this really quickly. So you can type %MD. MD is an abbreviation for markdown. When you type % something, it puts the rest of the cell in a certain special mode. And you can then, there's a markdown, it's kind of like, it's a really, really simple, plain text looking way of doing things. And it's because somebody else is using the same document. Let's see who. Min. No, it's okay. Actually, let me show you another thing, maybe. Are you using Google Chrome? Okay, watch this. Are you still looking at the worksheet? Oh, because if you bring up this spot on the worksheet, you should appear on the screen. Because it's what happens is if you type this, each person that's currently viewing the worksheet should appear along the side. Doesn't sound like it's working now. Is it working or you closed the worksheet?
Still motions.
Oh, it was a feature we added last week. Okay, in any case, let me hide that. Oh, somebody's doing it. There you are. So, so if you want to work with somebody else on a worksheet and they're not physically in the same place, you could use this. There's one little problem though. Each time you evaluate a cell, it like refreshes this, which is kind of annoying. It uses something called WebRTC, which is a new way of doing peer-to-peer video chat over the web. Okay, I'll make this disappear. Okay, so Markdown, it's documented at the link I give, and you can do things like consider some math, and you can put math like this, just using LaTeX. And when you hit Shift-Enter, what happens is the math gets turned into nice-looking math. And if you want to edit it, you double-click, and it comes back, and then you can continue editing. So that's one way to type up some of your solutions. Okay? So I just thought I'd point that out. And it has like, it'll do some syntax highlighting. Notice this turned blue, and that's the notation for a bulleted list and so on. There's other things you can do as well, like you can do percent, well, should be able to do percent LaTeX, and then literally just, it'll get turned into an image using LaTeX. Yeah, so this is a little image, and it was typeset using LaTeX. Okay, so there's that. For now, what you'll do is take this assignment and you'll put it in your project in a folder called homework, and then when you're done, you'll send me an email with a link to your solution. That's it. In the future, I'm going to be able to easily just browse all of these homework folders, but right now I need a link. It just will make it a little bit easier for me initially. I just want to do that at least the first time. So let me just say a little bit about uploading and downloading files, because that's unfortunately going to be necessary the first time around. So if you look at the list of files, where you click on Files in the upper left, when you put the mouse, and I totally understand this is not the best user interface, I'm kind of ashamed of it, but I'll fix it at some point. In any case, there's a little button, Download File, right here. So if you click on that, you can download the file to your computer. And once it's on your computer, if you open up another project, like maybe your own personal project, here's my personal private project related to this class. I'll just go into let me make a folder called homework. You could say new, and then here you could type in homework, and then click on folder. And what that will do is create a new folder called homework. Here it is. And then you can click on new again and upload the file that I just downloaded, which is in my downloads directory. There it is. And see, it appears here with a little check once it's uploaded. And now if you click files, you'll see that that file's there. You can now just click on it, do the problems, and then at some point, notice that there's a link in the URL at the top. Just send me that when you're done. Okay? So that's for now what we'll do. And I'll make it a little more automatic later. Okay, any questions about the homework process? And again, it's not due till January 22nd, so there's plenty of time to ask me questions. Future homeworks will be longer and more difficult. Any questions? Okay. Okay, so that's going over the homework. Okay, now all you have to do is talk about congruences. Let's see. One thing I should point out, in the shared project and also, so in the shared project right here, where it has homework, I've put a PDF version of the homework and also on the GitHub page. So you can click on that and print it if you want to have like a physical printout of the homework as well. And in general with worksheets, like if you do your homework and you're really paranoid that it's just going to disappear or that I'll never see it or whatever, you can click on the print button and that brings up this dialog. And then if you click on generate PDF, in a moment it'll pop up with the print version, which you can then send to a printer. Okay, and you can do that with any worksheet. And there you are. Apparently certain things look ugly, but All right, so now on to the lecture. So I'm going to show you kind of 2 or 3 things on the slides which are observations, and then we're going to just more carefully introduce you to some basics of abstract algebra and the integers modulo n, namely the first section of chapter 2, which I know half of you have already read, but half of you haven't. Okay, so first I just want to point out some surprising observations, just about things that you can do. Let's call them startling observations. Here's the first one. You can take a number with, say, 1,000 digits, any random number whatsoever, and quickly decide whether or not it's a prime number. You don't have to factor the number in order to do this. In fact, you can compute some big number like this. This one I just chose entirely at random. And then I called the isPrime function, and in a very little amount of, almost unnoticeable amount of time, a 20th of a second, it told me that this number is not prime. Yes? No, you just have it. Okay. It told me this number is not prime. But it did not tell me any particular prime factor. So it's kind of neat that you can have a big number, you can know for a fact it's definitely not prime, but you don't know anything really about its factorization, except that it factors. So the sort of idea that makes it possible to do this, there's like a whole world of ideas related to this problem, but it all involves modular arithmetic. That is, arithmetic with the integers modulo n, which is the main topic we're going to be discussing for the next for the next few lectures. By the way, for this particular number, I called a function trial division. What trial division does is it takes your number and then checks to see if 2 divides it, checks to see if 3 divides it, etc. It's how you might try to decide whether or not this number is prime. It actually kept checking until it got up to 5 million, a little over 5 million, and it found that divisor. And you won't be surprised that it doesn't actually take very long. So let's try this whole thing out. And then timing this, it took 0.3 seconds to try the primes up to 5.4 million, and it does find a divisor. So that number divides it. So it's not prime. That's not how it decided this number wasn't prime, though. It did a completely different thing. It basically took this number n equals big number, and then it took a theorem, which will be proved soon, which says that if n is a big prime, so if n is prime, then something cool. So it took n, it plugged it into whatever the something cool is, and it found that that wasn't true. Therefore, n wasn't prime. And the something cool is just some like little calculation you can do with n. So it just took that, plugged it in there, got nope, so not prime. And there's a lot of different possibilities for the something cool. So if you iterate this over and over again for various values of cool, then you get, each time you do it, increasing confidence. So if it keeps being true, then you get increasing confidence that your number is prime. And you can do it maybe, you can do some calculation like this maybe 50 times, and then the probability that your number is composite, but it appeared to be prime every single time, is far, far less than the probability that random bits were flipped in your computer via cosmic radiation. So you can be pretty confident that in fact your number is prime. There is a theorem now that's actually really recent, proved by 2 grad students and some professor in India, which says that there's a fast way of deciding with absolute certainty whether or not a number is prime. There's a deterministic polynomial time algorithm for deciding primality of numbers, one way or the other. It's a common topic that people often do a final project on, how that algorithm works. Okay, so that's the first observation. It's a strange thing, but you can take a number. So sometimes it's really obvious. You can take a number like that, and you can instantly say it's prime without knowing its factorization. You can instantly say it's not prime without knowing its factorization, right? You know it's not prime because of that 2 right there. You don't know its factorization. But even if I change this to another value, there are quick ways to decide whether or not that's prime without having to actually try divisors up to the square root. Just based on how many primes there are, do you think this, if you had to guess, would you say it's prime or not? Raise your hand if you think it's probably prime. Okay, raise your hand if you think it's probably composite. Numbers tend to be composite, so you're probably right. I, of course, have no idea because I made it up at random. 1, 2, 7, 4, 5, 7. It is not prime. And there is a factor command in here, by the way. So it's divisible by 11 in that case. All right, so that's first observation. And you'll understand more technically how it can be the case that you can be convinced that a very large number for which you have no hope of ever factoring it is definitely composite. So you'll be convinced of this soon enough in particular cases. Besides the computer says so, you'll actually know why it's reasonable to do such a calculation. Here's another observation which is perhaps less surprising, but you can take a big number with around 17 million digits, and you can figure out what the last few digits are very, very quickly. So this is kind of a bad illustration of that. I don't know, I don't really like the way I did this. But the idea is if you do the entire calculation, mod a small number, then you can quickly, let's just leave it at that. It's a fact that if you have some formula that gives you a big number and you want to know the last few digits of that number, you can do that very, very quickly by doing the entire calculation. Always, what you do is you do all of your arithmetic only keeping track of the last few digits, and it turns out that just works. Of course, we'll prove that. But basically, if you have two numbers, A and B, and you want to know what the last 10 digits of the sum is, you can just forget about everything except the last 10 digits and do the sum, and then take the last 10 digits of the result. If you want to know the last 10 digits of the product of two numbers, you could just take, even if you have 100-digit numbers, you just take the last 10 digits, multiply the numbers together, and look at the last 10 digits of the result, you'll get the right thing. It's kind of obvious if you think about explicitly how you multiply numbers. But you can replace 10 digits by other bases and stuff like that. Let me just show you what I mean by that. So let's say we have these two numbers, which I kind of just typed in at random. Just so it's not too hard to think about, for simplicity, let's say we're interested in the last 3 digits of this product. So we could just multiply the entire thing out and see the last 3 digits are 050. Now let's do the same thing, but let's just start with the last 3 digits in each case and multiply together and see what happens. Cool, look, the last 3 digits match up. So the point is, and this is just a special case of the fact that arithmetic with numbers modulo n, addition and multiplication is well defined. This is just the special case of that mod 1000. So if you want to figure out the last couple of digits of the product or sum of two numbers, just take the last couple of digits, do the product or sum, and then look at the last few digits of that. And this will always work. But it's just because, when you're computing this product or the sum, or whatever, you just work from the right to the left, and so all this other stuff just doesn't matter. Okay, so now let's move on. Now I'm going to do a little bit of abstract algebra, and right before I do that, I just want to make this object in Sage. It's just a Python class, integer mod ring 20. I'm going to define what the ring of integers modulo 20 is, formally from a math point of view. In Sage, it's just this thing. It has elements 0 through 19 inclusive, and when you do arithmetic, whenever you add or multiply, you just take the sum and then you reduce the result. You take the result, whatever it is, and then you divide it by 20 and take the remainder. So here, 7 plus 18, you get 25. Divide by 20 and take the remainder. That's 5. 3 times 8, that's 24. Divide by 20 and take the remainder. That's 4. So it gives you a way of combining via some operation any two elements of this list, or this set. Okay, so now done with the projector unless there are any questions. Actually, ask me a question or I refuse to continue. Yes?
I'm a little bit confused about the syntax of the mod function.
The what is the mod?
Mod function.
This right here?
No.
Or up higher? Right here.
Yeah.
Yes. Okay, so this notation means the remainder upon division by that. So let me.
I mean like a lower one, the mod
Right here. Oh, yeah. Okay, that's a good question. So when you write mod A comma B, this means the image of A in the ring of integers modulo B, which I'm about to define, but I haven't yet. But the most efficient way of doing this calculation is to work directly in the ring of integers modulo 10 to the 10. Let me just define that. So the exact thing I'm about to do is exactly what you don't understand yet. Perfect. Okay, any other questions? Yes? Factor? Did you say factor? Yes, yes. That will give the unique prime factorization of the number. So for example, if you're wondering what is the prime factorization of this year, there it is. It's 2 times 19 times 53. It gives you the unique expression of your number as a product of primes, possibly with exponents. If you put a number in here with 100 digits, it'll probably just sit there for hours and hours wasting CPU resources. People often do that, as I've observed. Okay, any other questions? And you, by the way, you can factor lots of things. Like, of course, you can factor integers. You can factor negative rational numbers. See, maybe not very impressive, but you can do it. You can factor polynomials. I guess that would be really, well, x cubed minus 1. So factor works on many things. Okay, so now let's move on to groups, rings, and fields. Don't really need this anymore.